Very good afternoon to all respected members who have gathered here for the today's research guest lecture on the following topic: testing and evaluation of material properties in core mechanical engineering using AI interface. So material testing forms the basic backbone of mechanical engineering design, manufacturing, quality assurance, and failure analysis. In today's guest lecture, we will explore how artificial intelligence is transforming conventional material testing methods into faster, smarter, and more accurate engineering solutions. Let us begin this exciting journey into AI assisted material evaluation. And coming over to the lecture overview, so, what we are going to explore in this segment today? In this session, we will discuss six major key areas. First thing, we are going to discuss about the existing thing that is already present in the mechanical engineering domain, various fundamentals and importance of material testing in core mechanical engineering. Second, what are the traditional testing methods used in mechanical engineering to evaluate the material property? The third one, integration of artificial intelligence and machine learning models in material evaluation. Fourth one, real world case studies demonstrating AI application and its capabilities. Fifth one, AI tools and software platforms used in materials research. And finally, we will look at the future trends and emerging opportunities in AI driven material science. Now let us discuss the foundation of mechanical engineering design. Why material testing matters very much. Material testing is highly essential for ensuring safety, reliability, and performance. Engineers generally rely on material property data to design the mechanical components that can withstand operational loads and environmental conditions. Testing supports quality assurance, certification, and regulatory compliance. It also helps in failure analysis, enabling engineers to understand why components fail and how to improve the future designs. With AI integration, material property prediction can achieve very high accuracy and also significantly reducing testing time and cost. Now let us see some of the traditional material testing methods that are already in use. Mechanical engineers commonly use several testing techniques. The tensile test evaluates the strength, ductility, and elastic properties. Hardness testing measures resistance to plastic deformation. Impact testing determines toughness and energy absorption. Fatigue testing studies behavior under cyclic loading conditions. Creep testing evaluates long-term deformation at elevated temperatures. Wear testing investigates tribological behavior and surface degradation. These methods have served industries successfully for many decades in the recent past. And what are some of the major limitations of traditional methods? Despite their importance, traditional testing methods have some of the major limitations that are listed out here. Many tests require considerable amount of time, especially fatigue and creep studies. Most are highly destructive in nature, meaning specimens cannot be reused. Human involvement introduces measurement errors and interpretation bias. Testing cost can be high due to equipment, manpower, and specimen preparation. In addition, data from different tests often remain isolated and difficult to correlate. These challenges create big opportunities for AI-driven solutions. Now let us get into AI interface in material testing. Artificial intelligence enhances every stage of material evaluation. Experimental data are collected and processed through feature extraction techniques. Machine learning models can learn relationship between material parameters and mechanical properties. Deep learning algorithms analyze the microstructure images automatically. Computer vision systems detect the cracks and defects in real time. Large language models assist researchers in literature review, experimental planning, and report preparation. Together, these technologies improve efficiency, accuracy, and decision making. Let us see now machine learning based material property prediction. Machine learning models can predict the material properties using existing experimental data. Input features may include chemical composition of the material, grain size of the material, heat treatment conditions, and processing parameters. Output can be a tensile strength, hardness, fatigue life, or fracture toughness. The models are trained using large number of data sets and validated using statistical measures such as root mean sum of square error and R squared values. In many studies, neural networks have predicted tensile strength with remarkable accuracy, reducing the need for extensive mechanical physical experimentation. So we now go with AI-driven microstructural analysis. Microstructure characterization traditionally requires significant manual effort and time, but AI-powered computer vision automates the grain size measurement, face identification, and defect detection. With the help of convolutional neural network algorithm, so it can analyze thousands of images rapidly and more consistently. AI systems can identify the following different microstructure of the material, say ferrite, perlite, martensite, as well as it will identify the cracks and porosity with high precision. This dramatically reduces the analysis time while improving repeatability and reliability. So far we have seen the special features of AI technology applicable to conventional core mechanical engineering field, say material testing and evaluation. Now, let us see the real world case studies, how AI technology can be lively used in simulating the material property behavior. Say, for example, glass fiber reinforced polymer composites. So, how to predict the tensile strength for this material? Let us take a practical example. In this study, artificial neural network were used to predict the ultimate tensile strength of glass fiber reinforced polymer composites. The model considered fiber orientation, volume fraction, curing temperature, and number of layer count. So using data from 180 experimental specimens, the artificial neural network achieved an R squared value of 0.972 and a very low prediction error. This approach can reduce the conventional destructive testing methods by approximately predicting 70% relative accuracy while accelerating the composite design compared to the old conventional methods. Next one, wear rate prediction in aluminum silicon carbide composites. Second case study focuses on aluminum metal matrix composites reinforced with silicon carbide particles. With the help of random forest machine learning algorithm, so this algorithm was used to train with the help of several parameters such as applied load, sliding speed, reinforcement percentage. So using these inputs, the model achieved excellent prediction accuracy with an R squared value of 0.964. Importantly, the AI system identified the optimum reinforcement content within minutes whereas the conventional experimentation required several weeks. So this is the difference between the AI interface technology and the conventional methods. Next one is fatigue life prediction model. The fatigue failure is a critical concern in mechanical engineering components. In this study, long short-term memory neural network were used to predict the fatigue life under variable loading conditions. The model learned loading history patterns and accurately estimated fatigue damage accumulation. Results showed an R-squared value of 0.983, outperforming the traditional fatigue prediction methods. Such models can be used for maintenance planning and reliability assessment of the material. Now we shall see AI tools and what are the so-called platforms. Several powerful tools support AI-assisted material testing. Python libraries such as scikit-learn, TensorFlow, PyTorch, and OpenCV are widely used on. Material databases like MathWeb and ASM handbooks provide valuable datasets. Specialized softwares include Dream.3D and Dragonfly support that is especially meant for microstructural analysis of the material. Cloud platforms such as Google Colab and AWS SageMaker facilitate model development and deployment. So these tools make AI more accessible to researchers and industry professionals alike. Now let us see implementation of AI-assisted technology in material testing. A structured workflow is highly essential for successful AI implementation. The process begins with defining the engineering problem. Next comes with data collection from experiments, literature, and simulation. Relevant features are selected and prepared for model training. Appropriate machine learning algorithms are chosen based on the application. Models are trained, optimized, and validated using unseen data. Finally, the solution is deployed for practical laboratory or industrial use. Let us now see the future trends. What are the various future trends regarding the material testing and evaluation using AI interface? The future of material testing is highly exciting. Generative AI will design new materials with targeted properties. Digital twins will continuously monitor the material behavior in real time. Autonomous laboratories will combine robotics and AI for self-directed experimentation. Federated learning will enable collaborative model development while preserving the data privacy. Explainable AI techniques will improve transparency and trust in predictions. Edge AI systems will bring intelligent quality monitoring directly to manufacturing environments. So these are some of the upcoming developments going to come in the future years. Before I close the session, I would like to describe the following key takeaways of today's session. To summarize the above information, AI does not replace engineers, it enhances the engineering capabilities. Machine learning models can predict material properties with very high accuracy. Computer vision automates microstructural characterization and defect detection. Deep learning extends predictive capabilities to complex phenomena such as fatigue. Open source AI tools make advanced technologies quite accessible to researchers worldwide. The future of material testing is intelligent, connected, autonomous, and data driven in nature. So, with the above information, I thank you all the members for your attention and participation. I hope that today's session has provided more number of valuable information into the integration of AI with material testing and evaluation. So I will leave a quote before I move on from today's session. Which is considered to be the best material in the universe? The best material is the one which we can easily predict, design, and validate intelligently as per the user requirements. So, with the above quote, once again I thank you and I wish all success in your engineering journey.